Hello, everyone. Welcome to the series Mud Talks, N+1 Lessons I've Learned Through a Decade in Artificial Learning with Professor George Montañez. My name is Vanessa Chu, Assistant Director in the Office of Alumni and Parent Relations. We thank you for attending today's event. This talk is being recorded and we distribute it after the event. Please feel free to type your questions in the Q&A box, not the chat, and we will try to get through as many questions as possible. Now, I'm going to turn it over to George to kick it off. George, thanks for being here today. The floor is yours.
All right, thank you for inviting me. Let me share my screen. Okay. And so, hi. So as mentioned, I'm George Montañez. I'm an assistant professor in computer science here at Harvey Mudd. And so today's talk is going to be a little bit different than the sorts of talks I usually give. Usually I will give a very narrow talk on one specific thing. And this is kind of a broader talk in the sense that I'm trying to share with you guys different lessons that I've learned through my time in artificial learning. And some of those lessons are going to be very specific things about how learning algorithms work. And other lessons are going to be maybe some broader, bigger picture lessons. And doing both of these, because of the nature of this talk, I'm not going to be able to get into depth in any particular topic. And so what that means is that I think of this as almost like a Costco sample tray talk, where you get a little bit of each thing, but maybe that's going to leave some of you wanting more. There will be some references throughout the talk, so maybe you can dig a little bit deeper if it interests you. But I just want to acknowledge that each of these lessons could be its own talk, and there are going to be very important things that have to do with artificial learning that we won't actually be able to cover just because of time constraints. So if I miss out on your favorite topic, I apologize in advance, okay? So let me tell you a little bit about who I am, how I got here. So I began my career in computer science. I did my undergrad at UC Riverside, eventually did a master's degree at Baylor University. And in both those places, I took machine learning and AI classes, which led me to pursue a PhD in machine learning at Carnegie Mellon University. And so the picture there is me and my firstborn. She was actually born my first semester there at Carnegie Mellon. And so I believe this picture, it looks like it's from about early 2012, right? And then after graduating in 2017, I went to work for a year at Microsoft. So I worked as a data scientist working on some of their ML software. And then I came here to Harvey Mudd College to be a professor, right? And since I've been here, I've been pursuing this sort of research in machine learning, artificial intelligence, with a group of very talented students known as the Amistad Lab. And so this is a subset of them. Believe it or not, there are even more students who are in the lab, not concurrently, right? We have 23 right now, but over the years, I've gotten to work with a lot of them. And a lot of the things I'm going to be talking about and papers I've been sharing, I will share, these students worked with me on. So I wanted to give this opportunity to highlight them because they're really a fantastic group of students. Okay, so let's start off with some terminology. You notice that in my talk title, I used artificial learning rather than artificial intelligence or machine learning. Maybe you've heard of computational intelligence. There are a lot of different phrases that roughly describe the same thing. And so one of the things I learned during my time in the PhD was that there are a lot of similarities between these different approaches to learning. So things like artificial intelligence, machine learning, et cetera. And so much so that I tend to think of it as just one broad area of computational learning or artificial learning, right? So for this talk, I'm going to use the phrase artificial learning to mean all of the above. It just means any sort of data-driven computational way of learning, okay? And if you notice on the slide, there is a little QR code that says scan me. And there is a reference. So this is my dissertation. If you scan that QR code, it'll actually bring you to the PDF of it. Throughout this talk, you're going to see QR codes and references to papers. These are going to be where my own research has interacted or intersected with the things I'm talking about. And so you can see that this is why I learned this particular lesson, or this is where perhaps I learned this particular lesson. That's not to say that there aren't a lot of other resources that you could look to, but this is just to give you guys a place to go if you want to dive a little bit deeper. Okay, so let's start with our first lesson, right? So our first lesson is that learning is about dependence relations. And the reason why this is the first lesson is that I think this is the most important lesson I learned about how machine learning works or artificial learning works during my time at Carnegie Mellon. And surprisingly, this lesson came at the end. It came towards the end of my PhD, but I think it's primary in importance. Okay, so let's start off concrete. We're trying to predict something typically in artificial learning. So we're going to do an example where we're trying to predict home prices based on square footage. And I acknowledge that when you're trying to price a home, there are more important things than just square footage, right? You have the zip code that it's in, you have the number of rooms, you have the condition of the home, but pretend that all we have access to is simply the square footage. And from that, we want to be able to learn to predict what is the likely price of this home. So we're going to need some data to do that, right? So we're going to need, for example, some data points. So imagine that we have our first data point, it's here at the origin, right? So if you have a 0 square foot home, you're going to say that the price is $0, which is good, right? Because we don't want people selling imaginary real estate. And maybe we have another data point where it's a little bit more than 0 square feet, and it's at the price of roughly $500,000. And we can refer to that as maybe the Southern California real estate market, right? And then in general, we have lots of other points that we observe. And so as we look at these points, we can see that it looks like they're roughly linearly correlated, right? And so we can make a guess that the relationship between the square footage and the price is actually some sort of linear relationship. And so we could draw a line and say, this is our guess at the relationship. Okay, we call that a hypothesis, right? So this is our guess. And in general, a hypothesis is represented in some sort of artificial learning model, right? Okay. And so what we have in artificial learning is we have some things that we observe, and then we have some things that we do not observe that we're trying to predict. In general, we observe some features. So we have this X, which is the set of features that we observe. In our previous example, this would have been the square footage. In general, there's more than one feature, right? You can have many features. And then we're trying to predict some response value or see what the response value is, which is, in our previous example, the price of the home. And so the task of artificial learning is typically to learn what this arrow relation is how do you get from features to some response value? How do you predict it? And in general, you're going to not just use the raw features, you're going to use some mathematical transformation of the features. Okay, so why is dependence important here? Well, the ability to actually learn this relationship hinges crucially on how much dependence there is between the features and the response, the thing that you're trying to learn. So in the case where there is no dependence, where the response is independent of the features, obviously you cannot learn that relationship because there is no relationship. So it doesn't matter how clever your learning algorithm is, you're not going to be able to learn that. And to the extent that these things are heavily dependent on one another, you're actually going to be successful in learning. So that's one aspect of dependence. There's also maybe like a vertical aspect where among your training examples, if you have 1 million training examples, but they're all just copies of the first training example, you're also not going to be able to really learn this relationship well. So what you want is you want independence among your training examples, but heavy dependence between the features and the response values. Okay. So lesson 2 that I learned, this was also kind of a big idea that helped shape my PhD thesis, was that all learning could be viewed as a search process. Okay. And this is helpful because I was looking at a lot of different disparate areas of learning, and I was trying to come up with some common way of representing them. And it occurred to me that people have viewed learning as a search for a long time. And so using that, I was actually able to formally prove things about how artificial learning works in general by using some of the theorems or proving some of the theorems that apply to search spaces rather than to particular types of machine learning algorithms, right? And so how does this work? Well, in learning, we must search through some subset of all the possible XY relationships, right? So between our features and our responses. And we use the training data as a guide. We need something to guide us through this enormous space of possible hypotheses. And we say that the good models are those that are able to predict well on new examples that we haven't seen in training, right? Or a model that is capable of doing some tasks. So maybe we're doing something like reinforcement learning, where we're trying to get a robot to do something well, right? And so those are going to be our good models. But in general, we have on the one side, we have our instance space. So this, to stick with our housing example, we can imagine that these are all the individual houses in an area. And now pretend that our task is not to predict the price, but to predict whether a house is overvalued or not, right, relative to the market. And so this becomes a binary classification task. On the right, we have hypotheses. It says which homes in the instance space are overvalued. And so each hypothesis is going to select out a different subset to say these are the overvalued homes. So we can imagine that hypothesis H1 selects out this yellowish oval and says these are the overpriced homes, right? Maybe they belong to a particular zip code. And the rest of them are not overvalued. So those are the negative examples. H3, on the other hand, maybe says that there's just one overpriced home, and maybe that belongs to some celebrity. And then H2 says maybe there's a group of 3 overpriced homes. But in general, what we're seeing is that each hypothesis is going to select out a different subset of the instance space. And what we're doing in the learning process is we're searching through the hypothesis space. We're trying to find a good hypothesis that could correctly label things, right? And so in general, we're either searching through this hypothesis space, or you can even say we're searching through a parameter space. So all learning falls under this rubric, all learning that I've encountered, I should say, right? So we've proven directly that you can cast lots of different types of learning as search, and I've yet to encounter a form of learning that can't be cast in this way of looking at things. Okay. So what is learning? Well, learning is a combination of recording the data that you're given and also applying your biases and assumptions to that data. And so biases here, I want to be careful using the word bias. Biases refers to a preference for some things over others. And typically when we use that, we talk about societal biases, right? Things like prejudice, prejudicial biases. Bias is a broader term, but it definitely includes as a subset prejudicial biases. But here I just mean the assumptions that you bring to the learning process. So on the left, we have 7 data points, and we show that they're connected by some roughly smooth curved line, and we're trying to predict what is the remainder of the line between the 2 maroon points, right? So where the line sits depends heavily on the data, right? I'm trying to fit those data points well. And so in some sense, the line is recording where those data points are. And then I have to predict what's going to happen where I don't observe anything. And so I'm going to bring an assumption. I'm going to say, you know, the rest of the line looks pretty smooth. And so maybe that middle portion is also some smooth interpolation between those points. But it doesn't necessarily have to be the case that my assumption holds. We can imagine that there's some world where there's some arbitrarily complex relation between those 2 points, right? So instead of just being a straight curved line, it is some very wavy, some highly complex shape, okay? And so what we see is that our final hypothesis is going to be a combination of these 2 things. It's going to be a combination of the training data that we observe, but also the assumptions and the biases that we bring to the process. The biases tell us how to interpret the data we see, right? Data doesn't interpret itself. It needs an algorithm to process it. It needs some sort of assumptions to prefer some hypotheses over others, okay? But these biases of all sorts can be easily corrupt if we're not careful. And so when we use the word bias in regular language, typically we're talking about societal or prejudicial biases. And so to use a high profile example, a few years ago, Microsoft released a chatbot, and chatbots again are very popular, that once it was released in the wild, within 16 hours, they had to shut it down because it began to use very biased, very offensive language, and it apparently became a Holocaust denier, as the example on the left shows. And so the problem here was that the training data that it was training on was essentially web data and user interactions. And this quickly led the system to exhibit 4chan level behavior, right? And so that was a problem with societal biases that were within the data. But we could also have problems with the biases that we bring to the algorithm process. So on the right, we have this other example of a system called PredPol, which is for predictive policing. And the assumption that the researchers made here is that where crime occurs and where it's likely to occur next, can be modeled using seismic algorithms for predicting earthquakes and aftershocks, right? And so this is an assumption that the researchers bring, and then they use that assumption to model given their data, right? one of the issues that arose from this is that if you have areas that are heavily policed historically, so places that are maybe low income or have these other factors, then those are going to be the areas that have higher incidence of crime because they're more heavily policed. So you have higher crime reporting. And so once you feed that back into the system, you get this prediction that the places where crimes occurred in the past are the places that they're going to occur in the future. So now you heavily police that area even more. So then you get more reporting of crime. And this could lead to a vicious spiral of for this model, right? And so the biases, the assumptions that we make, those could lead to problems as well. And so this is one of those little tidbits where we could spend the entire hour just talking about biases in learning, right? There are some books, if you guys are readers, Algorithms of Oppression, Weapons of Math Destruction. You can get lots of examples of how the biases and assumptions that go into these models can lead things astray. I've written a little bit about it with a collaborator at Baylor University. And so again, if you scan the QR code, you can go to one of my contributions in this area as well, okay? And so given how badly biases could steer us astray, we may be tempted to think, well, I don't want to put biases in my algorithm. I just want to make no assumptions whatsoever, right? And it turns out that we actually do need some biases for learning. They don't have to be prejudicial biases, and they shouldn't be, but we do need to make some assumptions, right? And there's a long history, a long literature going back to the 80s at least, of this, showing this need for biases in learning, right? And so it has been formally proven again and again just how much you need to actually add your own assumptions beyond what the training data shows you to be able to learn anything. And so if we have this naive view where we say, I don't want to make any assumptions, we show that it actually doesn't work. Learning won't work in that case, right? So if you had an unbiased learning algorithm, you could actually predict on new examples no better than you would by just flipping a coin, by randomly guessing. And furthermore, you're no more likely to discover a good model than you would be just picking uniformly at random models from the space of possible hypotheses, right? Okay. And so we have the biases. We also have the training data. And models, these artificial learning models, they absorb this data. So when we have our training examples, the training examples have the features and they have the responses. They have both parts because we're trying to learn the relationship. And some of the features might be very informative about that response value. So something like square footage is probably going to be pretty informative about the price of the home. But we may also have features that are not that informative. So you might have whether or not the address is a prime number, right? So we can imagine that that's not going to be very informative about the price of the home. And so every training example has this mixture of true information about the relationship we're trying to learn. We can consider that signal. And then there's also incidental details that may not matter or may just be noise, right? So that's the noise portion. And we have, on the other hand, our black box model that has a finite storage capacity. It can only learn so many things. And you can think of it as like a thumb drive. You're trying to fill in a thumb drive with some information from your training data. So what are you going to do? Well, the training process tries to extract this information and put it in the model, but we're hoping that we get mostly green. We're hoping we get mostly signal. The problem is we don't necessarily know ahead of time which of the parts is the signal and which of the parts is the noise, right? So the models are just going to absorb things from their training data. And this could be good or it could be bad, right? And we could see this actually in practice. So we have these generative AI models now, things like Midjourney and DALL-E, where you can type in a text prompt and it could produce these very stunning, very striking works of art. But some people have started to notice that when you produce these works of art, which ostensibly they're brand new things that no one has ever produced, right? They contain what appear to be artist signatures, right? And so while these aren't actual, they don't actually look like text signatures, it looks like scribbles. This is showing how the training data is reflected in the model, in its outputs, right? Because this model was trained on artwork, human-produced artwork, and human-produced artwork tends to contain signatures. This could be a problem because if you inspect your model, you may reveal things about your training data that you don't want people to know. And so there's a whole field called differential privacy where you're trying to produce models that and produce guarantees on what sorts of information you can actually learn about your training data given the model, right? You don't want to reveal things inadvertently. And when you have these very large generative models, they could actually store a lot of information. So you might get memorization, essentially, of aspects that aren't important for the actual relationship. And so you may wonder, well, is it only these large neural networks that do this? We wondered the same thing. So inspired by work from Zhang et al., which showed that neural networks can in fact memorize random data, we said, can very simple algorithms do the same sort of memorization? And so we did an experiment where we took a data set that had binary labels, and instead of the real binary labels, we erased them and we flipped a coin, an electronic coin, to come up with fake labels. And so we broke any dependence between the response values, the labels, and the features. And then we asked a learning algorithm to learn this relationship where there was no relationship to learn. So after training, we then presented just the features and said, can you reproduce the labels for these very simple algorithms? And so what you would expect is that because they're independent, you should essentially just be guessing randomly for producing the labels, right? Because there's no relationship to learn from the features. So you should expect 50% accuracy. And what we saw was that if this broad red line represents 50% accuracy, all of the models had greater than 50% accuracy, some of them strikingly greater. So if you see the kind of thicker yellow line, it was approaching 100% accuracy. So essentially it was memorizing all of its training data. And so memorization of training data is not just a problem for large models. It could even for decision trees, even for naive Bayes or for linear support vector classifiers, right? And so we see that this ability to store information, we want to rein it in somehow because we don't want to be able to do this. We don't want to be able to memorize noise in our data, right? And the larger the model capacity, the more this ability, the greater this ability to both learn complex relationships, but also potentially to learn noise. And so we want to make the model size congruent with the size of the relationship we're trying to learn. In other words, we don't want excess capacity. When we have this excess capacity, we have the danger of overfitting our data, which is where you're learning the noise and you're not really learning the signal. Right? So excess capacity is actually the enemy of learning and generalization. And generalization is just being able to predict beyond your training data, right? And so as practitioners, we have a few things that we can do to try to combat excess capacity. So we can use simpler models. So this is a sort of Occam's razor type of preference for simpler hypotheses. We could use regularization, which effectively clamps down on the ability or the capacity, the effective capacity of a model. We could use big data. So if you try to store a lot of training data in a small space, the algorithm's going to have to pick and choose what it remembers, what it stores. And so it's going to tend to prefer learning signal versus learning incidental detail, which won't actually help it in the end. And data augmentation is a way of just changing your data to effectively make more data, right? And so this is another way at which we combat excess capacity. Okay. So far, these 6 lessons that we've seen, these are all kind of drilling down on why machine learning works, why artificial learning algorithms do what they do. For the next lessons, let's take a step back and look at the field in general, right? And so lesson number 7 is going to be that the advances in artificial learning are nonlinear, but they're also very real. And what do I mean by nonlinear? It means that we can't say that there is a smooth progression of a smooth step-by-step progress every year where the capabilities of artificial learning are making breakthroughs every year. It's actually a very different picture where we have plateaus where there's not much real progress in the sense of breakthroughs, and then all of a sudden we'll get a new way of looking at things, a new approach that'll allow for a lot more capabilities within a short period of time. Okay, so we can go back even to 1956, which was where the phrase artificial intelligence was coined at the Dartmouth conference. And so this conference included luminaries in computer science, people like Claude Shannon, Herbert Simon, Alan Newell, Ray Solomonoff, Marvin Minsky. So it was kind of a who's who of who was thinking about these questions of machine intelligence. And here's what they wrote. They said, we propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956. And this was going to make an attempt to find how to make machines use language form abstractions and concepts, solve the kinds of problems now reserved for humans, and to improve themselves. And here's the kicker. They said, we think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. And so looking at just one of those things, so natural language processing. So they were essentially proposing that 10 men working for 2 months could solve NLP, right? And we know in hindsight that this was incredibly naive. It was incredibly overly optimistic. We've been working on this for 70 plus years, right? But there was some basis for their optimism, right? So we had Herbert Simon and Alan Newell. They came to the conference with a working chess playing machine, right? And they were working on another system, logic theorist, which was able to prove theorems. You had Claude Shannon, which in 1948 already was producing semi-stochastic text, right? And so he was using this bigram word process to generate text kind of mechanically. And this is a paragraph that he generated. The head and in frontal attack on an English writer, that the character of this point is therefore another method for the letters that the time of whoever told the problem were an unexpected. Okay, so this is, it's not meaningful, it's kind of gibberish, but there are portions of that that actually sound like an English sentence, right? So for example, you might be worried at this point about the safety of the English writer, right? So there are things in there which show that maybe, maybe with 2 more months and maybe 10 people, you can make real progress on this problem. But what we know is that it took us a very long time to get from that to what we have today, which is something like GPT-4, which is also doing semi-stochastic text generation based on the statistical patterns of words that occurred before. But here we have a poem on C++ memory management that I got from Melissa O'Neill, which says, in the realms of C++, a tale unfolds, a story of creation where memory molds, a dance of life, of objects' fate, allocation, construction, use, abate. Allocated first, memories reserved, a plot for objects their purpose served. Constructed then, initialized they stand, basic types may waver in this vast land. Okay, so it's not the best poetry I've ever heard, but it's still poetry, right? And so this is an impressive system that you give it a prompt and it could come up with a coherent poem about C++ memory management. But notice that it took us, again, 70 plus years to get to this point, and the progress from Shannon's original bigram model to this, it was not a straight path, right? So we had up to about, I would say maybe 5 years ago, we didn't have anything like GPT-4 that was able to produce text like this from a random prompt, right? And so we had long periods of plateaued progress, and then all of a sudden this sharp jump within the past 5 years where we have things like GPT-4, okay? And GPT-4 can not only write poetry, but according to OpenAI, it can now be 90% of humans on the SAT, right, as reported by CNBC. We have other systems which generate images. We talked about these before. There was this video a few weeks back by this group Corridor Crew where they had talked about always wanting to make an anime short story, but they didn't have the resources to hire a team of animators. And what they found is that they could use these generative AI methods to generate essentially an anime cartoon from their live action video. So they made a pipeline where they essentially just took the live video and then it turned it into anime, right? And so you could do a lot of very remarkable things. And again, these sorts of generative models, we're just starting to see them, right? This is a very recent thing within the past few years. And it seems that every year now we're getting kind of better and bigger models that are able to have even more capabilities, okay? So if you are Corridor Crew, you think that this is a very cool thing, perhaps. You're like, now I can finally make my anime video. If you are an animator, you might not think this is such a cool thing. You might think, well, what's gonna happen in the future where everyone can just produce videos from text? They won't need animators anymore. And this is a certain thing that whenever you have new technology, there's gonna be some sort of disruption. You're going to have certain areas, certain fields that may get lost, certain jobs that might be lost, but you also have new businesses that are created. And so if we take this picture on the left, this is of a human computer. So computer used to actually be a job title originally, right? And so if you've seen the movie Hidden Figures, you learn the story of these people who would do computations by hand for large scientific organizations, places like NASA, right? And I tell my students that somewhat ironically, computer is the first job that was automated out of existence by computers, right? When we have these new generative models, we're going to have some of the same things, right? We're going to have different areas are going to be displaced, but we're also going to have new businesses that are created. For computers, right? Think of all the businesses that were created around computers. My job included, right? I wouldn't be a computer science professor if it wasn't for computers. With these generative AI models, we're going to have new businesses, things like Lensa AI. So apparently that was the top grossing app recently. And so as we mechanize aspects of human cognition, as we are able to recreate, whether or not we do them super well, as long as they're good enough, we can now compose those together to put them together into new business models. And we can do things that weren't economically feasible before. So going back to the example of the Corridor Crew, the reason why they didn't make their anime video originally wasn't because there weren't animators around, it's because they couldn't afford animators for this one project. But now that they had this tool, it allowed them to do it for much cheaper. They were able to do animation in a place where it wasn't economically feasible before. And so the way I see it is that maybe there could be room for not necessarily displacing people, but just expanding the areas where we could apply these techniques to places where it wouldn't have been economically feasible before. And so I think of examples of things like travel agents, right? So we have Expedia, we have Travelocity, but yet we still have travel agents around because there's a place for people who don't want to necessarily book their own travel. And so in the same way, even if we have AI animation, it could be the case that there is some specific specialized type of animation that people want from humans, right? Or we can think of poetry generation. I don't know if I'd necessarily want to read an entire book of poems generated by an AI, but I would perhaps want to read a book that was generated by a human where those poems are reflecting their actual experiences and teaching me things about human nature, right? And so what do we learn from this, right? So we learn that there's going to be disruption. There's also going to be hype around these things. So as we get systems like Lensa AI, we're going to see that people get very excited. One group's going to get very excited about this, but there's going to be other groups who are afraid and concerned, right? Validly concerned about these sorts of things. But in general, there are hype cycles, right? So if the progress is real, the hype cycles are also real. So when you get a new technology, it's going to grow in visibility over time. And eventually you're going to reach what is called the peak of inflated expectations, right? So this is the Gartner hype cycle, where everyone thinks this is either the end of the world or this is the greatest thing ever. And then some of the limitations of these new technologies start to become apparent, and they start to lose some of their sheen, right? And over time, people start to think, oh, this technology isn't actually what we thought it was going to be. And then we go through a trough of disillusionment. But as time progresses, we start to say, well, maybe this technology doesn't do everything, but it can do some things perhaps well. And so we start to find the appropriate context for various technologies. And we approach what's called the plateau of productivity, or as my former mentor at Baylor University, Bob Marks, used to say, it approaches the asymptote of reality, right? It's getting closer to that. And so for us, we're now inundated with these generative AI models. I would say that we are maybe right here. So either we're at the peak of inflated expectations, or we're maybe starting to move just past it as some of the limitations are starting to be known. And it should be said that these systems have very real limitations. So take ChatGPT, for example. So systems like ChatGPT, GPT-4, they make up facts, right? So if you ask it about something, it could very persuasively make up something that you think is an actual real fact. So ask it about the history of bears in space, and it will give you a very detailed explanation on how the Russians sent bears to space. It will give you the names of the various bears, and it will also give you references. It'll give you hyperlinks to articles that talk about these bears in space. The problem is that if you click on the hyperlinks, you'll get a 404 error. They're not actually real hyperlinks, right? And so it can hallucinate, it can make up these things very persuasively, very convincingly. And because of this and many other problems with these generative models, now people are starting to take concerns about them seriously, right? And so maybe we're moving past the peak. I don't know. We'll see, and time will tell. Okay. And so I want to leave you guys with one last lesson, right? Let's see where we're at on time. Okay. So one last lesson is that given all this talk about prediction, and that's what artificial learning is all about, we can't actually predict very well when breakthroughs are going to occur. The progress is nonlinear, and so we don't know when or where this next breakthrough is going to occur. And there are many examples of this in the history of artificial learning. We can talk about AI winters, so times where the hype reached its highest point, and then everyone became disappointed when the systems didn't deliver on that hype. And so funding was cut, people stopped working on things. And then later on, a different approach was tried, and then real progress was made. And we weren't necessarily able to predict ahead of time which sub-area this was going to happen in. So one example that I really like that's near and dear to me is the example of Jeff Hinton and his collaborators. So there's a great story on Chronicle, which talks about how they stuck with an idea that everybody else had essentially discarded, right? And this idea was that of the neural network. And so neural networks have a long history, started off with Rosenblatt proposing the single perceptron. And the single perceptron was able to take some inputs, do a mathematical function on it, and produce an output. Rosenblatt apparently had a very forceful personality. He was able to get people to buy into this idea. In 1969, Minsky and Papert wrote a book called Perceptrons, where they showed that a single perceptron couldn't even learn an XOR function. So it wasn't even able to learn simple relationships. And so neural perceptrons, they kind of fell out of favor for a while. And then later on, people like Werbos and others figured out that you could actually connect perceptrons together and form what's called a neural network, right? And so you put these things together, and now you can layer them. And so you end up with a network of perceptrons. And then they came up with efficient or effective algorithms to train them, things like backpropagation. And so then you had even more capabilities with these neural networks. And eventually that reached hype. They showed that neural networks could actually learn any arbitrary function arbitrarily well if you had a big enough network. And so again, these fell out of favor, right? They were prone to overfitting. There was a time where nobody really wanted neural networks anymore, and connectionist models of learning fell out of favor, right? Everyone thought the statistical models of learning were much better, things that were bottom up, things like support vector machines, Bayesian methods, et cetera. But Jeff Hinton and his collaborators, they stuck with it. They thought there is something to neural networks. And so what they ended up doing was making their neural networks very deep, right? And we got something called deep learning. And although they had a lot of trouble getting funding for this work, a group came along, CFAR, and actually funded it because they thought, you know what, this is kind of an unorthodox approach. And even though others don't think this is going to be worth anything, maybe it's worth funding this kind of unorthodox project. And as we know in hindsight, Hinton won the Turing Award in 2019, along with Yoshua Bengio and Yann LeCun. And the Turing Award is essentially the Nobel Prize of computing. And so all of these generative AI models that I'm talking about, the ones that have these really impressive capabilities, these are based on deep learning. These trace their roots back to the exploratory work done by Hinton and his colleagues, right? And so this is one example. The history of science is filled with examples of breakthroughs coming where people least expected it. A lot of times these are discoveries that people just kind of stumble upon by accident, right? And so we don't have a really good track record of predicting where these future breakthroughs are going to occur. And so to me, the way that we hedge against this is by having a diversity of approaches and perspectives, right? Because we don't know which one is essentially going to pay off in the end. Pakalin and Bhattacharya, they wrote about this in the sense of scientific stagnation. So they think that scientific progress as a whole has stagnated because we have people not working on a variety of areas, but people tend to congregate to where the breakthroughs already occurred. And the reason for that is because now we're obsessed with citations, right? We have publish or perish, and really get cited or perish. And so if you want to get your work cited, you're going to have to work in an area that a lot of other people are working in. And so we get this congregation of researchers to the hot areas, and those hot areas by definition are going to be where the breakthroughs have already occurred. And so we end up just getting incremental advances. My mentor, Bob Marks, he used to liken it to a child soccer game where the whole team is just wherever the ball goes, that's where the team goes, right? That's kind of science in a sense, especially in artificial learning, right? And so what they were suggesting is maybe we should reward exploration, not just the exploitation of breakthroughs that already occurred, because we don't know where the breakthroughs are going to occur next, right? And it turns out that we have very little tolerance for this. So diversity of thought, diversity of approaches, and funding for it. It's very hard to get funded if you have unorthodox or different ideas, right? Again, this could be a whole talk, but even places that are typically open-minded, places like MUD, for example, I think of machine learning and artificial learning in a different way than a lot of other people. I've gotten pushback here at MUD for kind of my unorthodox way of thinking about data science and various things. So what do you do about that? So my encouragement to you, and I'll end the talk with this, is that you should defy convention, right? It's going to come at a personal cost, perhaps. And in my case, it definitely has come at a personal cost. In Hinton's case, it came at a personal career cost. But in the end, it was the right thing for him to do because he had the vision. He saw that he was going to be able to eventually do something where others didn't share that same vision. And so I would say if you have the vision, then go for it, right? We need more exploration scientifically, right? And so I will leave you with that. Thank you for your attention. Thank you for your time. And I believe we will answer questions now. So thank you guys again.
Thank you, George. We do have a few questions. Let's see. How do you think about the language we use to describe what AI systems and computers do? For example, we say artificial learning, and we talk about computers thinking, and we hope they understand our values. Are these literal ascriptions of learning and thinking and understanding, or are they metaphors or something else?
Yeah, so I think the language is unfortunate. So there's this thing called seductive semantics, right? It's kind of nicer to talk about learning. Like it's more exciting to talk about machines learning than talking about statistical correlations, which is really what they're doing under the hood. This is the terminology that we've inherited. And whenever you're working in a field, you have to use the terminology that the field uses. So this is why I use those terms. I don't think they're actually learning. I don't think they're actually thinking in any kind of meaningful way. But I have no other way to describe it. So maybe if I spent some time, I could come up with another set of vocabulary, but then I'd have to convince everybody else to use my set of vocabulary. So for the time being, I will say learning. And then if you ask me specifically, like what I think it's doing under the hood, I could explain that in detail.
Great, thank you. Next question, what is the typical mistake you've seen in students when walking into AI? What is usually your recommendation to someone starting in the field?
Yeah, so I would say, students and everyone tends to underestimate kind of the mathematical underpinnings of artificial learning in the sense that they mistake math for magic, right? And maybe because we're at MUD, maybe I could blame Prof. Benjamin for this. But when you really dig down to the nitty gritty of how these systems work, it's basically just applied math. It's applied statistics. And so I think if you want to really excel in the field of artificial learning, your best bet is to learn all the math you can. So I would say if you have the choice of learning all the computation or programming you can versus all the math, I would say learn the math because the math is going to enable you to actually create the algorithms that maybe other people will code, right? Both are important. I'm not saying that coding isn't important. Again, I teach CS, but I think that without the mathematical basis, you can't really do as much in this field. So I would say not knowing ahead of time that this is basically applied statistics, which I didn't know when I started my PhD. I thought, oh, I have a background in computer science, I should be good, right? And then I walk into this applied statistics program, but it's a learning experience.
Got it, thank you. Our next question, so in the mid to late 1980s, Lisp was the focus of AI R&D. Are there any remnants of that earlier work in the field today?
Yeah, so I would say that these kind of classical approaches to AI specifically, these are usually involving symbolic ways of representing learning. So you try to learn things in a very logical way. You use these logical programming languages. Yes, so in robotics, right, there's a joke that robotics is where these classical methods have migrated to, right? So you need to prove things very formally if you have robots interacting with humans. So there's definitely a place for that. But I would say even in just AI or artificial learning in general, there's now this return to trying to incorporate symbolic methods of learning back with these bottom-up statistical approaches, because the bottom-up statistical approaches don't get you everything, right? And so now people are thinking, well, maybe we need both. Maybe we need the logical, symbolic ways of thinking of artificial learning along with the bottom-up statistical data-driven ways, right? And so there's some very interesting work in the field trying to combine these sub-symbolic approaches with symbolic approaches.
Great, thank you. Our next question, is deep learning a pathway to self-aware software?
I don't know, right? So you're asking me to put on my my prophet hat, right? I can't predict the future. I would say I don't think so. I'm personally haven't been persuaded that this is the path to that. I think that there are kind of unique aspects that I know from my first person experience. So I know what it is to have volition. I know what it is to have agency. When I look at these statistical correlation machines, I don't see that same thing. And so I haven't been persuaded that this is the case, but I'm kind of agnostic on the question. I don't know, right? Like, I've been surprised by things in the past. I've learned N+1 lessons. This may be another lesson that I learn in the future. But if I had to place a bet today, I would maybe place the bet on no, but I'm open to being persuaded otherwise.
Thank you. Our next question, how do you think about the marriage between capitalism and AI?
Yeah, so that is a question that is outside of my area of expertise. Definitely AI or artificial learning is a lucrative area. So it definitely powers businesses, right? There's also aspects that you can argue are exploitative about it. I'm not the person who would want to give a talk on that particular thing, but there are a lot of people in HSA who could actually probably give you some very keen insights about that relationship.
Thank you. Our next question, what are some strategies you are seeing in the research community to combat learned bias in AI tools? Thinking of things like misidentifying people of color because of a too small training set of people, skin tones, gender.
That's a great question. So there's a lot of work on this by a lot of different people, a lot of different research groups, and it's very important work. To continue with the theme of the talk of tying it back to things I've personally worked on, we had a paper at the IEEE, the AAAI ACM conference on artificial intelligence, ethics, and society, where we produced learning methods essentially for trying to find representational biases inside training data. So a lot of the times these methods will take training data, they'll process it, and then they'll notice in the outputs that it's actually biased in some way, and they'll try to mitigate that on the outputs or in the algorithm. What we did is we said, maybe you're starting off with an unrepresentative sample to begin with. How would you know that? And so we came up with statistical tests. This is work with William Yick, Lim Manthes, Serafini, and Timothy Lindsay. And we showed that you could actually create a system for looking at biases before you ever get to the training process. So this is definitely something that a lot of people are working on, including Amistad Lab, but it's something that maybe more people should work on because this is actually a very real problem that we have in artificial learning.
Thank you so much. Excuse me. Our next question, it seems that the most talked about areas of successfully application of AI are in language and image processing, where patterns tend to be highly repeated. What's your view on applying current AI technology to high noise to signal fields areas such as economics and finance?
Yeah, so there definitely that is a keen observation, right? That we have the biggest breakthroughs, particularly in these sorts of areas. I would also add a third area where we've had breakthroughs. I didn't talk about it personally, but in the realm of game playing. So we have things like AlphaGo, AlphaZero that are able to play games like chess and Go and StarCraft better than human beings can. But definitely the kind of perception and the statistical correlation areas. So things like images, there's a lot of statistical correlation between pixels, or things like language, there's a lot of statistical correlation between words. Something like finance, again, I'm not an economist. I don't know how random the stock market is. Some would argue that it's just a random walk. Others would argue that there are underlying dynamics that could be learned. I do know that there's a whole area of quantitative finance where people are applying data-driven methods to try to produce money. And given that their firms are still up, I would say that maybe they're having some success in that. But I don't know. I don't know to what extent we would actually be able to learn something like whether I should sell a stock or buy a stock. Yeah.
Great, thank you. Our next question, what is the role of genetic or biological algorithms in artificial learning, if any?
So I think that some of the learning methods are inspired by things in biology, like very loosely inspired. So if we talk about neural networks that we talked about earlier, those are supposed to be modeled by a neuron in the brain, right? So perceptron is a play on the word neuron. And so these things are supposed to kind of be inspired by that. We have other learning methods that maybe use genetic algorithms for trying to train models. Those are, again, inspired loosely by biological processes. I don't see a very strong connection. I think it's mostly just like a light inspiration, but I could be wrong. There could be areas that I'm unaware of where they're using this thing directly. I know at CMU, there was a group by Ziv Bar Joseph. He was the principal investigator of that group, where they actually did look towards how nature's algorithms work. And so what I mean is they looked at biology and they said, how are biological systems accomplishing these things? And we're just going to copy the algorithms that the biology did. And so that was specifically for some computer science things, but also for learning things, right? And so there's at least one group that does that, but I don't know how widespread that is. I don't encounter that the same way that I encounter these kind of generative AI models that are using just, gradient descent and things like that for training, right?
Thank you. Can ML be used effectively in educational platforms without any misinformation?
So I think that there is a place for learning methods in education, but because it's the same as saying there's a place for artificial learning in medicine, because the stakes are so high, we have to be very careful. And so I think when it involves students, particularly minor students, some of these dangers that we have can be amplified, right? And so while there is maybe space for exploring this, I would say we should do it very cautiously. We shouldn't just say, hey, we have a new technology, let's throw it at everything. But there could be space for it. Even something like ChatGPT, right? So we have this tool that can generate text, and there's discussion here at the college and across colleges across the nation of whether we should use this as a productivity tool, right? Because ChatGPT does some things well. Maybe we should leverage that and use our kind of unique human capabilities where we excel, use ChatGPT where it excels, and together maybe we could be more productive. And so I think the same thing could be said about education. There's a space for it perhaps, but we have to be very careful, right?
Right. So we do have someone who took a machine learning class about 4 years ago, where the professor tended to tell everyone to just trust the data and the algorithm, which essentially meant like don't question the answer. Yeah. So to them, this seems problematic. How do you personally work to minimize that type of potential worship of the data algorithm and incentivize people in the industry to apply critical thinking to assess whether or not this makes sense or if this is right morally and ethically?
Yeah, so I would say that's an unfortunate thing that the professor said, because you should never just blindly trust an algorithm's outputs, right? Even if you are sure that the algorithm is doing the thing you want it to do, your data could be skewed in some way. Moreover, you don't know what biases, what perceptions, what assumptions went into making that algorithm. So I think Kathy O'Neill said that these models are essentially biases encoded in math. Right. And so that's how we should view them. We should be very skeptical of them. And I think that we have, as a culture, maybe lost some of this respect for skepticism. But I think, especially in this area, we need to revive it. We need to have a very healthy skepticism of what these methods can do. And I like that I think the word worship was used, right? Mm-hmm. I think that's really how people start to see these things. And I've given talks elsewhere where I've likened it almost to idolatry, right? In the sense of idolatry is when you ascribe powers to things that don't necessarily have them, right? And you worship them. And I think for AI, people start to overestimate their capabilities to the point where it becomes you place trust in something that maybe shouldn't have your trust, right? And so in this case, I think there is a general awareness, especially in the field, right? People are very aware of the limitations, biases of these models, but we can do more to convince the public and to share with the public some of these limitations. And that's for us, the people who know how these things work, to share that information with people when we're talking to our friends. Our friends will say, hey, I'm doing this thing with DALL-E. we can start a conversation. What does that mean? You know, how is this thing trained? Where is it getting its training data from, et cetera?
Thank you. So we are coming up on the hour. So for our last question, what's the most exciting application of AI you've encountered?
So me, I'm actually super geeking out about these generative art models. So I think that it's super cool in the sense that you can conjure up the thing that you're trying to think of in kind of very surprising ways, right? And there are issues with it. So I'm not saying that these things are issue free, but the fact that my kids can type in prompts and come up with artwork that they wouldn't be able to draw right now. Like, this is a force multiplier for how much art we can put into the world, for better or for worse, right? So for me, I think they're really cool. So I like them. For other people, it might be things like ChatGPT. I don't know. I think that they're all exciting. I think that anytime we actually have real breakthroughs, that's an important thing to celebrate, but it's not something to worship either, right?
Right. Well, George, I want to thank you for joining us today and for sharing your knowledge and insights with us. Thank you to our audience for your questions and for attending this event. We will follow up within the next week with a recorded video. Next up on Mud Talks, we have the power of the prototyping mindset, how embodied questions can help you build a meaningful life and career with Professor Josh Brake on Thursday, April 12th at 5 p.m. Pacific time. If you are interested in being a Mud Talk speaker, please contact us at alumni@hmc.edu. All future events can be found on our website, alumni.hmc.edu. Have a great night, everyone, and we'll see you next time.
All right. Thank you, guys.
Thanks, George.